So we covered linear regression, which is the single most famous and most used model in statistics. However, linear regression is not a model that you can use in every case. So in linear regression, we make the assumption that the error is normally distributed. And this means that the response variable, the predictions we make, they can take any value from minus infinity to positive infinity on the line of real numbers. However, this doesn't always make sense. There are domains where the response variable needs to be restricted. So let's say that you're modeling sports outcomes. It wouldn't make sense to say that you're predicting 3.2 goals, for example. The number of goals in a football game has to be an integer. Or maybe you are facing a classification problem, let's say binary classification. Again, it doesn't make sense to predict a real number. You'd need to predict true or false. So how can we deal with this in the context of statistical modeling? There are various models for dealing with the case of the response being non-normal or not on the line of real numbers. The most common answer to these issues is the generalized linear model. So the generalized linear model, as the name implies, is a generalization of linear regression. So we assume that there is a linear relationship between the input and the output. However, we no longer assume that the error is normally distributed. So let's take a look at these equations. In the original linear regression model, the equation looks like this. The expectation of y, our response, our target variable, is equal to this expression, which is the intercept plus the coefficient of the first variable times the first variable plus blah blah blah, the coefficient of the nth variable times the nth variable. So in the generalized linear model, the difference is in this, the g function, which we call the link function. So this is a function that's applied in the response in order to ensure that this no longer varies from minus infinity to positive infinity. So this expression can, but eventually this function transforms the response so that it's bounded in a range. The most famous generalized linear model is probably Poisson regression. So in Poisson regression, we deal with count data. So we're dealing with positive integers, including 0, or we're dealing with rates. In most cases, we deal with count data. In the case that we have a contingency table, explained in the next slide, where we have only categorical variables as inputs, we call this model a log linear model. But Poisson regression and log linear models are exactly the same. It's just that we use the term log linear model when talking about the case where we have only categorical variables. So we assume that the response variable follows a Poisson distribution. And remember this link function I mentioned earlier, function g? Well, for Poisson regression, that's the logarithm function. So we use the natural logarithm, which means that the log of the response equals this expression. Hence, if we want to get the actual value of the response, we have to exponentiate this expression, which means that we have to interpret results in a slightly different way. Because when we interpret the coefficients, our model is no longer a simple additive one, it's an exponentiated model. So why do we care about Poisson regression? Well, the Poisson distribution is all about integers. And there are many domains where we actually have to use integers. So we mentioned sporting outcomes, accidents, arrivals in hospitals, the number of times someone will access an application per day. So the Poisson distribution is a natural distribution to use for those cases. And I mentioned that we can also use the Poisson regression model for rates. So in order to do this, we just divide the count by time. So if we care about the number of traffic accidents per year or per month or the births per 1,000 people, then we get rates, where again we can model using Poisson regression. And I mentioned contingency table, and I also mentioned that a Poisson regression model for contingency tables is called a log linear model. So contingency table is a table like this. You have two categorical variables or more categorical variables, and the cells of the table are frequencies. So this could be a data set that describes the preferences of the different genders as to what they buy from a cafe shop. And you can see that males, they bought 592 cups of coffee, and females, they bought 410 cups of coffee. So we use a log linear model in this case to understand whether there's any relationship between gender and the type of product they buy. So Poisson regression, like all statistical models, makes some assumptions. The first one that's very important is that the response variable needs to be either 0 or a positive integer. If that's not the case, then you can't use Poisson regression. Another strong assumption is that the variance needs to be equal to the mean. And if this assumption is violated, then what we can do is we use the negative binomial regression. And there are some other models related to Poisson regression, like zero-inflated models or Handel models, which are used in cases where the number of zeros in our dataset is considerably large. These models are a bit more advanced, but it's good to mention them. So how can you assess the performance of Poisson regression? Unfortunately, in the generalized linear model, we no longer have R squared. So in linear regression, we had the metric of R squared, which is translated also as the percentage of the variance explained. So unfortunately, that's no longer the case. What we have is the pseudo R squared, where the pseudo R squared is a metric defined as 1 minus the log likelihood of our model over the log likelihood of the null model. So the null model is a model that's using only the intercept. Again, if you remember in linear regression, we performed a similar hypothesis test of our model against the intercept-only model. So in statistics, in general, we want to make sure that our model performs better than some baseline, and the most natural baseline to use is an intercept-only model that predicts the mean. So that's one metric to use. However, it does not have exactly the same interpretation as R squared, as the percentage variance explained. So this might be a bit problematic. The Akaike information criterion is a metric that's used to compare between different models. It's defined as 2 times k minus 2 times the natural logarithm of the likelihood of the model, and k in this case refers to the total number of variables. So this metric is penalizing models that have more variables, but at the same time it's awarding a score for the models that have better likelihood. And finally, we can use some other regression metrics, like the ones we used for machine learning models, like the root mean squared error, the mean absolute error, or the correlation between the true and the predicted values. Like with all kinds of statistical models, we have to use different metrics and plots in order to assess the performance. However, Poisson regression, like in linear regression, can give us back tests, significance tests for the significance of the different coefficients. So we can understand which variables are important. There's an important note we need to make here around the interpretation of the coefficients of linear regression and Poisson regression. So in linear regression, let's say we have a model like this one. So we have sales equals the intercept plus income and age. So in this case, we could interpret the coefficient as follows. We could say that 1 point increase in income increases sales by 1.2, keeping all other variables constant. However, the interpretation of coefficients in Poisson regression is different. So in Poisson regression, we no longer have the sales, but we have the logarithm of the sales. So this expression turns into this. Sales equals the exponent of this expression, which breaks down as a multiplicative expression. This means that 1 point increase in income in this model causes a 3.32 times increase in sales, because now these terms they multiply with each other. So be very careful with interpretations of the coefficients in each model. Logistic regression is another famous model. We already covered logistic regression in machine learning. It is considered by some a machine learning model. However, logistic regression originates in statistics. And in logistic regression, we're trying to solve a binary classification problem. For example, whether it will rain tomorrow or not, the gender of someone, the credit score, whether we should let someone alone or not, etc. Logistic regression can be derived in different ways. It was originally formulated, however, by David Cox in 1958. Some of the other derivations include logistic regression being represented as a neural network without a hidden layer, or in natural language processing, it can be derived from the principles of maximum entropy, hence the name maximum entropy classifier for logistic regression, which is used quite often in natural language processing. However, the original model, developed by David Cox, a prominent statistician, models logistic regression as a generalized linear model. So the distribution of our data is binomial, and what we're modeling here is the log odds of the probability of the true class over the probability of the negative class. So, if you remember this expression from the machine learning lectures, this is simply the logistic function. So this expression makes sure that the log odds of true over false lie in the range between 0 and 1. So effectively, our expression predicts a probability. The output of logistic regression is a probability which we can then turn into a classifier by just choosing a threshold, which most often is the threshold of 0.5. Anything above 0.5 belongs to the positive class, anything below 0.5 belongs to the negative class. And in order to measure the performance of logistic regression, we can use standard classification metrics like the accuracy, the F1 measure, the ROC curve, things which we already covered in the session for classification and for machine learning metrics.